Okay.
All right, welcome back, everybody. Our next speaker this afternoon is Thomas Weighill from UNC Greensboro, and he's going to talk about coarse homotopy groups of warped cones. All yours, Thomas.
Thanks very much, and thank you to the organizers for the opportunity to speak here. So I'm going to start talking about things in coarse geometry, and rather than try and explain everything in the field, I'm just going to pull from it what I need. And the sort of main important topic, or so main sort of most central notion in coarse geometry is this idea of coarse equivalence. So a coarse equivalence is supposed to be some equivalence between spaces that, instead of looking at micro details, sort of takes a large scale point of view. The one that sort of is always shown to people the first time they see this is that the real lines are equivalent to the integers. Here we're not thinking of them so much as groups as spaces. And the sort of intuition is that real line is kind of this continuous line. The integers lie along this line. But if you were to walk back far enough away, those lines, those little points in Z would merge together and they would look kind of like the real line. Now, not everything is coarsely equivalent to everything else. All bounded spaces are coarsely equivalent to each other. But for example, Zn is coarsely equivalent to Zm if and only if n equals m, and this you can prove using some large-scale dimension arguments, which are sort of similar to the dimension arguments you might see in classical topology. And then maybe the most important coarse equivalence is a whole class of equivalences, which is that a space, let's say a geodesic proper metric space, X is coarsely equivalent to G if G acts on X, where G is some group. If G acts on X geometrically. So that just for us can mean properly discontinuously, co-compactly by isometries. And this is important because this allows us to sort of talk about groups and the spaces they act on almost in the same breath. And this is really where sort of the power of coarse geometry as it's applied to geometric group theory comes in. Sort of a slightly less well-known type of equivalence, but one which has definitely been around since the very early stages of this field, of coarse geometry, is coarse homotopy equivalence. And sort of, this is a much weaker notion. For example, Rn is coarsely homotopy equivalent to an n-dimensional manifold M if M is Hadamard, so negatively curved, complete, and simply connected. And in particular, Euclidean space of the nth dimension is coarse homotopy equivalent to hyperbolic space. And these are not coarsely equivalent because one is a Gromov hyperbolic space and one isn't. So this is really kind of a weak equivalence. So if it's so weak, what is it good for? Well, this was applied very early on in coarse geometry to prove the coarse Baum-Connes conjecture for spaces. So the coarse Baum-Connes conjecture is this coarsified conjecture, which shouldn't really be called a conjecture. It's false. There are counterexamples. But when it's true, it implies things about the Novikov conjecture, say if it's true for a group with its word metric. And the sort of fact is that for the early versions of coarse homotopy, at least, if X is coarse homotopy equivalent to Y and X satisfies this conjecture, that implies that Y does. And this gave some really early proofs for this conjecture for sort of some nice classes of spaces, for example, Hadamard manifolds. We just saw that they're basically Euclidean from this perspective, so that makes sense. Yu proved it for spaces with Lipschitz good covers. This was sort of the first in a series of strengthening sort of, or I should say weaker and weaker conditions that imply the coarse Baum-Connes conjecture, eventually arriving to embeddability in Hilbert space. And Gromov hyperbolic spaces, I find this one very interesting because what you actually do to prove this is you prove that a Gromov hyperbolic space is coarsely homotopy equivalent to the open cone over its boundary, which is kind of a nice strategy of attack. And then these open cones have nice behavior, so you can prove something about X. Now, sort of, there's the old definitions of coarse homotopy, which kind of existed for those applications. And recently it's kind of been reinvented by Mitchener, Norouzizadeh, and Schick, but also sold simultaneously by Bunke and Engel. And their full names will appear in a subsequent slide, so don't worry. And they do so by using a cylinder object. So what's the idea? Well, the idea is to borrow homotopy theory from topology. homotopy theory and topology is really just based on this one object, which is not this one object, but it's based very strongly on this object of the cylinder object, right? You have a space X, you cross it with an interval and you get this space here. So this is X cross I. And you can sort of build a lot of homotopy theory from that. Well, what they did is they introduced the cylinder object. And the cylinder object is parameterized. It has a particular function. You start with a metric space and you choose a function, and typically this will be coarse. I'll define that later, but for the definition, it's not important. This is just some kind of control over what's happening. And you define the P cylinder using this complicated expression, but I'm just going to draw a picture. So this is coarse geometry. So the space in question is really big that you're trying to build the cylinder over. And what you do is you, instead of building the cylinder sort of up and down, you start with a small piece and then you add more and more of your space. So as you're expanding, you're adding more and more, and each of these slices looks like its projection down here. So it's, instead of having a cylinder which is just finite width, you've got a cylinder that opens out more and more and includes more and more of the space. So there are some natural inclusions here. If this is the cylinder object over X, you have two natural inclusions here and here. So you can put X in there, you can put X in there, basically. I'm not sure if the picture makes that extremely obvious, but this is basically the idea. And this is the formula if you're interested. So the same way you have inclusions here to top and bottom, you have inclusions like this. And this allows us to define what coarse homotopy is. So I'm not going to write out the definition, I'm just going to draw a coarse homotopy. But to do so, I need to introduce sort of two basic types of maps. So what is a homotopy? A homotopy in classical sort of topology is a map from X cross I to Y. Not just any map, it has to be continuous, right? We have to have like a topological control over it. And in coarse geometry, the right notion is not continuous because we're kind of zooming out past all these little local behaviors. The right notion is bornologous or coarse. So a map is bornologous if for every fixed R, points which are R apart can only get so far apart in the image. So a more descriptive term here is uniformly expansive. And the map is coarse if the inverse image of every bounded set is bounded. Not uniformly so, but it's like a properness condition. Some people call this metrically proper. So we're going to consider coarse maps, and coarse maps include bornologous maps. And a coarse homotopy is going to be a coarse map like this. So H is going to be a coarse homotopy from the cylinder object IPX into Y. So there's a choice here made by the P, but for a Y class of spaces, you don't have to worry too much about this P function. And then there are the inclusions we just spoke about. And so we say that H is from, HI0 to HI1. In other words, those two maps are coarsely homotopic. So to sort of help us visualize what this looks like in practice, I've got a very simple example here. So I'm going to consider two maps from the positive reals to this first quadrant. The first one just puts the positive reals at the bottom here. The second one is going to put the positive reals along this y-axis here. And I claim that these two maps are coarsely homotopic. Well, they're properly homotopic. They actually are homotopic. And indeed, they're coarsely homotopic. I can just interpolate between them like this, right? And you may recognize this picture. This kind of looks like a cone over the interval. And that's kind of the idea you should have here. The difference between this and just proper homotopy or continuous homotopy is I can sort of ignore an entire hole here. So I can be very discontinuous here. And sort of pretend there's like a hole in the surface I'm putting between these two. And that's totally fine as long as the hole has bounded diameter. So this does not need to be a continuous map. It's just an interpolation that's sort of bounded in its distortion. So attached to this idea of coarse homotopy, there are these coarse homotopy groups, which were introduced by Mitchener and two collaborators in a recent paper. And the definition is down here, but it's kind of hard to read. So rather than sort of read that to you, I'm just going to try and compare it to topology. So in topology, coarse homotopy groups, well, we have a base point x0 and we have loops, right? And the loops are sort of what forms the group. Well, in the coarse setting, points are kind of negligible. So we want something better as our points. And so the choice that these authors made was that the points are going to be maps, coarse maps, from the positive reals into X. So for those who like geometric group theory, you may think of this as a base ray, right? If you're doing, say, semi-stability or fundamental groups at infinity, you're basing your whole construction at a ray. And loops are just going to be homotopies from this thing to itself. So things that look like this. Continuing on. And then up to homotopies that preserve that base ray, right? Path homotopies should be homotopies between these kind of cones that still keep the base ray fixed. And that's everything that's contained in the definition. And the authors go on to prove a very nice result, which is that if you take a space M, like some finite simplicial complex, so I'm going to draw a torus, even though you should imagine some triangulation, we can take the cone over that. So this is a compact topological space. It's trivial from the large scale point of view. We can promote it to having some good behavior by taking the cone. So the cone is just embedded in some sufficiently high dimensional Euclidean space and take all the lines through it from the origin so that you get this kind of opening up effect. So what this is doing is it's kind of taking all the little small scale behaviors that the torus maybe had. The torus is pretty simple, but maybe a puncture or something, and it's promoting them to bigger and bigger scales as you go along. And what they proved is that if you take the coarse fundamental group of this cone, it's the same thing as the fundamental group of what's going on downstairs, right? And this seems extremely nice, but it's actually kind of non-trivial if you think about R squared. So R squared is actually the same thing up to coarse equivalence as the cone over S1, right? If you have a cone, you can just flatten it down to make R squared. And so it's not completely obvious that the coarse fundamental group based at, say, this ray, this is a valid base ray in coarse geometry, it doesn't have to be isometric, just has to be a coarse map, that fundamental group, coarse fundamental group based there is the same as, say, a straight line coming from the origin. But the result of these authors implies that. And so it's something you would hope is true, but it takes a bit of work. So what I was interested in recently is what happens to this coarse fundamental group under group actions, especially because in topology, group actions are extremely important for coarse fundamental groups. So kind of the first thing you learn, so one of the earliest things you learn in algebraic topology is you learn to compute you learn to compute pi1 of the circle by putting it into a sequence that looks like this. So you have pi1 of the real line, pi1 of the circle that injects into Z, which is it surjects onto Z, which is the group that acts on R, the covering group, the deck transformation group. And this allows you to calculate pi1 of S1. And I showed that you get exactly that kind of situation down here under some conditions. And the conditions you need are as follows. So you need a group acting by isometries. Can weaken that slightly if you need to. And then you need the sort of equivalent of a properly discontinuous action. So if you sort of remember what a properly discontinuous action is, a properly discontinuous action is sort of one that moves points some uniform distance. What we need here is actually a coarse version of that. Instead of everything moves points a little bit of distance, the group moves points further and further as you escape compact sets, and actually more generally as you escape orbits of compact sets. And then if you remember from covering theory, you can't say much if your total space is not connected. Some things can happen and you have to account for it. So I have this connectedness condition, which I won't say in detail, but basically it means that you can find coarse homotopies between base rays. So you should think of this as path connected. And I call it coarsely semi-stable because in a lot of cases, it's not equivalent to semi-stability, but you can prove one direction. If you have what sort of group theorists would call semi-stability, then for the space it's acting on, you have coarse semi-stability. And you get this. The only sort of piece that's not really well explained here is what is this Q doing here? This is not how I originally wrote down pi1 coarse. I just wrote pi1 coarse without the Q. And this is a small little technical consideration. You actually need to consider pi1 coarse. You need to consider not just maps which are coarse as your homotopies, let's say from R plus or from IP R plus. You actually need to consider maps which are coarse when composed with this map. So it's kind of a restriction. And this seems kind of arbitrary, but it's actually a sort of a special case of some general theory that Bunke and Engel have been working on in their big monograph. It's actually what they would call a map between Bornological coarse spaces with a particular Bornology. So I just want to quickly change gears to warped cones, which is this type of space that's gained a lot of recent interest. It was introduced by Rowe, and the definition is that if you have a finitely generated group acting on a compact space, that induces an action just on the level sets of your cone that you build. And you're going to warp the metric on this cone by the group in the following sense. You put a new metric on, which is the biggest metric that is both bounded by the original metric and allows you to jump between generators for a price of 1 distance. So this seems kind of complicated, but in practice, it's pretty easy. If you want to get from a point X to a point Y, you're allowed to jump along generators for the cost of 1, and then you're allowed to walk for the cost of whatever that distance really is. So in this case, the distance between X and Y is at most 16. And you just have to look over all possible jumps and walks to see which is the best one, and that's your distance. So you're kind of building shortcuts into your space. Now, I'm not really going to look at the bottom 2 of these results, but this one is a big motivator. This is by Damian Zavitsky, which says that if the action of G has certain properties, if it has a spectral gap, and G is good enough, then this warp cone does not satisfy the coarse Baum-Connes conjecture. So counterexamples to this conjecture are kind of highly prized, and this is a very nice way to generate them. This is a big reason why there's a lot of interest in warp cones. They were introduced in 2003 or 5, but they kind of lay dormant for a long time, and then suddenly sort of 3 or 4 archive papers appeared proving these kind of results. So the main result for this talk is a result about warp cones, which just says if you have G acting on a manifold M, then you get the short exact sequence down here, which is, here is the sort of original cone. Here is the warped cone. Over here, that's pi1 coarse, and G fits into this picture over here. This is the group that's acting. And this is not an immediate application of what I spoke about previously, because a warp cone is very different to an orbit space. When you're taking a group action on a space and you're quotienting out by that, the whole orbits are collapsed to a point. Whereas in a warp cone, it still costs you some distance to move along the orbit. So unless your group is finite, the orbit space, in this case, that would be the quotient of OM by G, is not the same thing as the warped space. However, we can get this result using a cool idea of Zavitsky and Wu, which is that there is an action of G on this product. It's not the one you maybe think of immediately, but there is one. It's kind of this twisted one, such that you can write down the warped cone as an actual quotient of this action. Okay, and so what that means is, like, I can treat my warp cone as a quotient of some space that's a product that I understand. And it turns out that actually dealing with this product is pretty easy, and you're able to fit together everything into this short exact sequence. And then this turns out to be just the same thing as pi1 coarse of OM. And that's how you get the result. So as an application, we get sort of this basic rigidity result, which is, as I'll show in a minute, is pretty much known, which is that if you have 2 groups acting on 2 manifolds and they make 2 warp cones that happen to be coarsely homotopic, then you get an isomorphism between your groups. Right? So this is a nice rigidity result. And it kind of resembles this result of Vigolo, a recent result, which this isn't exactly stated in the paper. This is kind of a corollary of some powerful machinery they have there. But they have the same thing, except the only differences are that they force finitely presentedness, and they also require coarsely equivalent, not just coarsely homotopic. And that's all. That's where I'd like to end. Thank you very much.
All right, thanks. Do we have any questions for Thomas?
Could you say a little more about the coarsely semi-stable at infinity?
Yes. So for basically what you require is that for any two base rays that you can fit a coarse homotopy between them. That's the condition that you really need. And this kind of makes sense because rays are like points. Now for the theorem to hold, you actually need this homotopy to be a little bit stronger. You need it to not only avoid bounded sets, you need it to avoid orbits of bounded sets. But I didn't really mention that in the theorem because it would have made it too long. And the way it relates to normal semistability is if you have a length space like a geodesic space, let's say if any two rays are properly homotopic. So this is the condition of what you might call semistability if it was a CW complex with a group action. If they're actually properly homotopic, that implies the existence of these coarse homotopies. And the only thing to check really is that the proper homotopy is very continuous, but it might not respect the distances. It might move faster and faster as you go out. And you have to just check that you can rescale it so that you get a coarse homotopy.
Okay, thank you.
Okay. I have a question that goes way back to some of your early slides. And when you were talking about Hadamard manifolds.
Yeah.
Are you talking about, are those Riemannian or can they be Hadamard manifolds in the cat zero sense?
I think this result is only for, the proof only goes through for manifolds because actually the two maps can be described as, it's literally the exponential map and the log map, but you have to scale one of them. And I'm not sure if I can remember on the spot, but I think you have to scale one of them by something. So at least the proof that I know only works for Rn.
Yeah, the reason I ask is there are these famous Davis manifolds. You know, there are these non-positively curved aspherical manifolds whose universal covers are not homeomorphic to Rn, and they have non-trivial fundamental group at infinity. So I was wondering if those universal covers could possibly be coarsely proper homotopy equivalent to Rn. Given that there's this exotic.
Interesting.
Yeah.
If you can send me some references, that would be really great because I've been trying to work out the exact relationship between the fundamental group at infinity and the coarse fundamental group. And in one direction, there's like a reasonable relationship. And in the other direction, you start to get, it's not obvious to me. Initially, my suspicion was that they're isomorphic. I'm now moving further and further away. And it might be that those examples you're talking about are exactly the kind of places to probe this distinction.
Okay, sure. Yeah, I'd be happy to send you some places to look there. All right. Any other questions for Thomas?
I have sort of a more naive question. This isn't even necessarily related to the main point of the talk, but just about coarse topology in general. And it kind of came to me while listening to the talk. So, you know, in geometric topology, often we kind of make this main distinction between manifolds and singular spaces or just non-manifolds. Is there any sort of coarse notion of like a coarse manifold versus a coarse singular space? Or, you know, because we lose that fine structure, that's just kind of a meaningless question?
I'll tell you, I don't know if there's such a thing as a coarse manifold. I'm sure there are people who have tried. For every notion, there exists someone trying to define the coarse notion and study it. What I have seen is coarse CW complexes. So these play an important role in Bunker and Engel's homotopy theory and the original stuff that Mitchener did with coarse homology theory. But these are weird. These are kind of gluings of infinite cells in well-defined ways. They're like big cells with well-defined behavior. I think in general, the question of like locally X coarsifies to what X, I think that's really tough.
Thanks.
Any other questions? All right, let's thank Thomas for a really interesting talk.